Good morning. Welcome to this course Electricity and Magnetism. I am Dr. Rajkishore Mishra. I have got my PhD degree from IIT Kharagpur in physics, and presently I am working as a faculty in Maharshi College of Natural Law, Bhubaneswar. Today we will discuss about electric field, field lines, flux, potential, and if possible then Gauss law and its applications. So, let us start with electric charge. What is electric charge? Electric charge is a fundamental and characteristics property of elementary particles. We know matter consists of atoms, and atom consists of three elementary particles: proton, electron and neutron. And proton and electron, they have electric charge. Protons are positively charged, electrons are negatively charged, and the force between two charged particles is called electrostatic force. Here we will deal with the properties and behavior of electric charge at rest. So, it is static electricity. Then coming to these properties of electric charge, charge is, as already I have told, that it is a very fundamental property of elementary particles. If we consider two electrons, we already know that every particle or matter has mass, and because of mass two bodies attract each other by gravitational force according to Newton's law of gravitation. So, if we place two electrons separated by 1 centimeter, we would get a gravitational force of order 10 to the power minus 67 Newton between them. This is the attractive force between them, but when we place them, they actually repel each other with a force of order of around 10 to the power minus 24 Newton. So, this extra 10 to the power 43 Newton comes from something else than the gravitational force. This is electrostatic force, which is, as you can see, it is billion times stronger than gravitational force, and this electric force arises because of charge of elementary particles, right. Well, as I have told that there exist two types of charges, positive charge and negative charge, and protons have positive charge, electrons have negative charge. And unlike gravitational force, this electrostatic force is both attractive and repulsive in nature. Like charges repel, unlike charges attract, and this is a very strong force. And one more property of charge is it is quantized in nature, it is discrete, because the basic unit of charge is the charge of electron. For a proton it is, we write plus E, for electron it is minus E, and its value in SI system is 1.6 into 10 to the power minus 19 coulomb. So, we do not get a fraction of electron charge. Therefore, every time we get charge in a body, it is an integral multiple of this electron charge. Therefore, we say charge is quantized nature. So, any charge is in fact n times the charge of electron. So, at microscopic level charge is quantized, but this charge value is so small. If we take 1 coulomb charge, then it would contain approximately 10 to the power 18 number of electrons. It is huge. So, at macroscopic level we do not bother about this discreteness or quantized nature of electronic charge or charge as a whole, and at macroscopic level we can even consider a continuous charge distribution. Okay. And as Newton's law of gravitation is the fundamental law that decides what is the gravitational force between two masses, here we have a very fundamental law called Coulomb's law, which decides the force between two point charges. We say them point charge when their size is negligibly small in comparison to the distance between them. Coulomb's law says that when two point charges, say q1 and q2, are separated by a distance r, then the electrostatic force between them is proportional to the product of the charges, and inversely proportional to the square of the distance between them. And this force obviously proportional to q1 into q2 by r square, or F is equal to some constant c into q1 q2 by r square. As you have remembered that in Newton's law of gravitation, here the constant was a universal gravitational constant. We write it as capital G. It is a universal constant because its value is same everywhere in the universe. But here this proportionality constant depends upon the nature of the medium where the charge resides, and the value of C in SI system is 1 by 4 pi epsilon. 4 pi epsilon. Here epsilon is called permittivity of the medium. Permittivity of the medium. And for air or vacuum, this permittivity is called epsilon naught. And the value of 1 by 4 pi epsilon naught is equal to 9 into 10 to the power 9 Newton meter square by Coulomb square. This is the value of 1 by 4 pi epsilon 0, the proportionality constant. So, in SI system in air medium, 2 point charges experience electrostatic force of magnitude 1 by 4 pi epsilon naught q1 q2 by r square. This is the magnitude of the force. F is equal to 1 by 4 pi epsilon naught q1 q2 by r square. And like gravitational force, this electrostatic force is also a central force, means the force acts along the line joining the two charge particles. So, if we consider a unit vector r cap along the line joining the two charges, that is along r, then in vector form we should write the Coulomb's law as F is equal to 1 by 4 pi epsilon naught q1 q2 by r square into r cap, because every vector can be represented as the product of its magnitude and a unit vector along that direction. So, this is the electrostatic force between 2 point charges. Now, we will discuss about electric field. What do you mean by field? Let us consider a charge, a point charge, an isolated point charge rather, where no other charge exists in its vicinity. Let this point charge is capital Q, and if we place another charge, say small q, near it at a distance r from it, this charge experiences an electric force because of this charge capital Q. Now, let us imagine if we remove this charge q here, what exists there? Something exists there. That something is electric field, which is, rather we would say, is the electrical effect of this charge q, capital Q. And this electrical effect is incorporated in a physical entity called electric field, So, electric field is rather an elegant way of expressing electrical environment of a charge, the charge which is the source of this electrical effect. This charge is called source charge, which produces this electrical effect around it, which we call electric field. And in this electric field, when we put a charge, another charge, say small q, it is experiencing a force. So, here field is mediating between capital and q and small q for their interaction. So, it is a kind of force at a distance. We know force at contact, we push, we pull, we get a force or we impart a force, it is contact force, but sun is at far away from us. Still earth is experiencing gravitational force due to sun. It is because of the field, it is force at distance. So a mass produces a gravitational effect around it, it is gravitational field. When another mass enters into this gravitational field, it experiences a force, that is gravitational force. Similarly, a charge produces an electric field around it. When another charge enters into this region, it experiences an electric force. So we say that if this electric field as E, then the force experienced by this charge small q is F is equal to q into E, and we write it as a vector quantity, this E, electric field. So from this equation we can get an operational definition of electric field as force divided by charge. Of course, this charge is a positive charge. So it is force per unit positive charge. But once again, this is operational definition of electric field shows how to determine electric field at a region or at a point. But when you put a charge q, rather we call it as a test charge. This charge is called test charge because it is used to test the electric field at a point in the region, and this charge is the source charge which is producing the electric field around it. So when we place this test charge q, this source charge is imparting an electrical force on it. At the same time, according to Newton's third law, this test charge is also imparting a force on the source charge. So the position of the source charge may be disturbed. But our intention is to find what is the effect of this source charge at its original configuration or original position. So to not to disturb this position of the charge, source charge, the test charge should be extremely small, negligibly small, but the ratio of F by Q is a finite quantity. So the more accurate definition of electric field, the strength of electric field or electric field intensity is like this: limit q tends to 0, F by Q. F is the electric force, electrostatic force on this test charge small q. The test charge here is a extremely small positive charge. This is the definition of electric field. So, but I must add here, this concept of electric field or field rather is not a purely mathematical construct, it is a physical entity, and we can understand it better when we deal with electromagnetic wave. This field transfers electric energy. In electromagnetic wave, electromagnetic field carries energy in space and it takes some time to be transferred from one point to another. So, it is a physical entity. So, it is an elegant way in understanding the electrical behavior of static charges, and we will discuss it more in electromagnetic wave theory and other chapters. So, this is our electric field, and let us calculate what is the strength of electric field or electric field intensity due to an isolated point charge capital Q, that is the source charge. So, obviously the force on this test charge, as we have written this equation, we just replace Q1 Q2 by capital Q and small q, capital Q and small q. This is the force expressed by the test charge small q. Suppose this capital Q is placed at point O and test charge is placed at point A, and our intention is to find electric field at A due to the source charge capital Q. So, from the definition of electric field, we can write E is equal to F by Q and limit Q tends to 0, and from this equation we divide it by small q and q cancels out, and we are left with electric field is equal to 1 by 4 pi epsilon naught capital Q by r square into r cap. So, this is the electric field intensity or strength of electric field at a point or at a distance r from a source charge isolated point charge capital Q. If there exists a system of charges, number of point charges, then we apply a superposition principle. That is, we will find the electric field due to each individual charge at a point and we add them vectorically, as electric field is a vector quantity. The resultant electric field gives you the electric field due to the system of charges or distribution of charges. As I have told earlier, that at macroscopic level numerous electronic charges constitute a total charge. Therefore, we can take or we can look upon the distribution of charge often as continuous charge distribution. The charge may be continuously distributed over a surface, it may be distributed over a volume, it may be distributed over a line or a wire, so on. So, the resultant electric field is always obtained due to this distribution of charges using the superposition principle, and as it is a vector quantity, its direction must be specified. The test charge we consider as a small positive charge, a negligibly small positive charge. So, if our source is a positive charge, obviously it will repel and the direction of field is away from the source charge. If the source charge is a negative one, then obviously it will attract and the direction of field will be towards the negative charge or the source charge. So, the direction of electric field is away from the source charge and towards the away from the source charge when the source charge is positive, and it is towards the charge when the source charge is negative. Okay. I have just told you that the electric field should not be considered as only purely a mathematical construct, rather it is a physical entity. And to elaborate more, we can consider that in physics, particularly in physics, we say a field when a physical quantity has well defined value at every point in space and it may vary from point to point. Okay. And if that physical quantity is a vector quantity, we call it as a vector field, and if that physical quantity is a scalar quantity, we call that a scalar field, and our electric field is a vector field. Okay. And the entire electrical environment of a source charge or a distribution of source charge is completely characterized by two such fields. One is obviously the vector field, electric field, another is a scalar field, that is electric potential, which we will discuss later. Now, there is a way also we can visualize the field, a pictorial representation of electric field by simple vector diagram. We know a vector is represented by an arrow such that the length of the arrow is proportional to the magnitude of the quantity, and head of the arrow gives the direction of the quantity. And if I place a source charge, say point charge, which is a positive charge, and I draw the electric field due to this charge in a vectorial form or a pictorial form, then I must represent it like an arrow whose length is gradually reducing as we move away from the charge, because the field is inversely proportional to r square. So, this arrow, the length of the arrow gradually decreases. It is like this. This is the direction in which a small test positive charge would experience the force. Okay. So, this is a visual description of electric field, and we often call these as field lines, electric field lines, which are diverging away from a positive source charge. And If the source charge is negative 1, obviously the test charge will get attracted and the direction of these field lines will be towards the charge. Okay? And these are called field lines. So, for an isolated positive charge it is like this, for an isolated negative charge it will be directed towards the negative charge. It will be directed towards the negative charge. And if there exists more than 2 charges, the field lines would be like this. If we consider it as a dipole, generally 2 equal and opposite charges separated by a small distance, then the field lines are curved lines. So that if we draw a tangent at any point to these field lines, it would give the direction of resultant electric field at that point. Therefore, we would define field lines as the imaginary curves, right. These are the imaginary curves drawn in the field such that tangent to the line of force at any point gives the direction of resultant electric field at that point. And obviously, these field lines have a source, they start from positive charge and end at negative charge. If there is no negative charge, it would extend to infinity, and if there is no positive charge, it would come from infinity. So, electric lines, field lines, it was first introduced by Faraday as lines of force. We would prefer to say these are field lines rather, and these field lines have a source, that is positive charge, they have a sink, that is negative charge. They never curl, they never complete curl. Electric field lines has a very important property, they never completely curl around something. They start from some point and end at other point, start from positive charge and end at negative charge. This is a very important property of field lines. And two field lines in a electric field never intersect each other, because for example, if I draw these two field lines and if they intersect, then obviously at point of intersection I can draw two tangents to the two lines of force, and they would give two different directions of same electric field at same point, which is absurd. Therefore, two field lines never intersect each other. This is property of electric field lines. Now, let us discuss about electric flux. What is electric flux? Let us take an example, physically observable example. Suppose we consider a liquid is flowing through a cross section with a velocity v, and the area of this cross section is say ds. So, obviously, in 1 second the liquid would move a length v, and this cylinder will have a volume v into area ds. This is the volume of liquid that is flowing through this cross section through this area ds in unit time. This is called the flux of liquid that is flowing through the area per unit time, v into ds. Obviously, if I place this area like this, not perpendicular to the velocity, not normal to the surface, this this surface element is not normal to the velocity, then I will have a projection of the surface ds which is perpendicular to the velocity, and if this angle is theta, then it will be d cos theta, and in that case our flux of liquid flowing through the area is v ds cos theta. And in vector form, this velocity flux or liquid flux would be written as v dot ds. We know that two vectors have a dot product to give rise to a scalar quantity. This v dot ds gives the rate of flow. that is the total flux, liquid flux, and this ds is a vector here, area. We take this surface element as a vector, and the direction of vector is always along the outward normal to the area. If this is an area, ds, its direction is along the outward normal. N cap is a unit vector along outward normal to the area ds. Okay. And this is v dot ds. Drawing the same analogy, if we want to see how much electric flux is passing through an elementary area ds, then we should write it as E dot ds. It is the dot product of electric field and area element. In fact, it is proportional to the number of lines of force passing through that area. Here it is a physically observable one in case of liquid, we do not observe it in electric field. It is just, we will imagine the total number of lines of force passing through the area is proportional to this E dot ds, which is flux. Okay. As we can draw infinite number of lines, we do not say it is equal to the number of lines of force, but it is proportional to the number of lines of force. More number of lines of force means more flux through an area. And this flux due to a charge, point charge through an area is the number of lines of force passing through the area. I have drawn here a cone with its vertex at the charge, source charge q. If I consider an area here, the total flux here is same as the total flux here. Okay. Because these two areas subtend a same 3-dimensional angle at the vertex of the cone, that we say a solid angle. We write it as d omega, we say it as solid angle. In a plane, we know the arc of a circle subtends an angle at the center, we call it as plane angle, and this plane angle is arc by radius, L by r. When in 3 dimension we just imagine a cone, the base of the cone subtending the angle at the vertex, it is in 3 dimension, and this 3-dimensional angle is solid angle. Here in a plane, the unit angle whose unit is radian is that angle when the length of arc is equal to radius, r by r is equal to 1. So, an arc length equal to the radius subtends unit plane angle. Similarly, in 3 dimension, a surface area, this is a surface area, this surface area of value equal to radius square, surface area of a sphere, the surface element of a sphere, the surface element of part of a sphere whose area equal to r square would subtend the solid angle at the center as unit solid angle. Okay. So, obviously, a sphere has total surface area 4 pi times r square. So, the entire sphere would subtend the solid angle at the center as 4 pi. In fact, any closed surface would subtend the same solid angle 4 pi at an internal point. This is the concept of solid angle, and its unit is steradian. Okay. And the total solid angle obtained by the closed surface at an internal point is 4 pi, just as in a plane it is 2 pi. The total plane angle obtained by a circle or a closed curve, it is 2 pi, and here it is 4 pi. You just imagine the cone just expanding to form a sphere. Okay. So, that this solid angle goes on increasing and the total solid angle becomes 4 pi. And this, so obviously, as the unit solid angle is the area of the surface sphere, the area of the surface element of the sphere having r square subtends the unit solid angle. So, the solid angle d omega would be equal to, if the area is ds, and the radius is r, it would be equal to ds by r square. Okay. As here d theta is equal to dl by r in plane in 3 dimension, d omega is equal to ds by r square, the surface area by radius square. And if this surface area is not normal to the radius, if it makes an angle say theta, it is not normal to the radius, then we can have a projection of this surface ds along perpendicular to the radius, that is ds cos theta. So, if the surface element is not perpendicular to the radius, then our solid angle will be the projection of ds along the surface which is normal to the radius divided by r square, ds cos theta by r square. This is what the concept of solid angle. So, one same solid angle makes equal number of lines of force wherever may be the area, because the area is proportional to area is proportional to r square, while field is inversely proportional to r square. So, when we calculate the flux E dot ds, the r square cancels out and the flux is same. So, we conclude that electric flux through an area is E dot ds, that is E ds cos theta, which can be written as E cos theta into ds or E into ds cos theta. So, we can explain it in two ways. E cos theta is the normal component of electric field to the surface. So, it is the product of normal component of electric field and the surface element, or the electric field into the projection of surface element in direction perpendicular to the r. Okay. So, this is what the electric flux through a surface element. Now, let us consider the total electric flux passing through. Let us consider total electric flux passing through any closed surface when the closed surface encloses a point charge q. Suppose this is a charge q, and we consider a sphere of radius r that encloses this point charge q, and this point charge is located at its center O. Then if we consider a surface element from this sphere, say of area say delta s is a small surface element, then the flux through this delta s will be E dot delta s, as it is obvious the direction of area and electric field are in the same direction. So, the dot product gives you E delta s cos 0 is 1, it is E delta s. And what is E here? It is 1 by 4 pi epsilon 0 q by r square into delta s. Now, what would be the total flux through the sphere, through this closed surface? That would be summation of all these E dot delta s if we divide the sphere into many such surface elements and then sum over it. That would give you the total electric flux, that is summation of E dot delta s. And as the sphere, every point on the sphere is equidistant from the charge. So, this r is a constant quantity and the sum is over the delta s. The sum is over delta s, that is the total surface area of the sphere. And what is that total surface area of the sphere? That is 4 pi r square. So, it is equal to 1 by 4 pi epsilon 0 q by r square into 4 pi r square. This r square 4 pi cancels out, and we are left with q by epsilon 0. So, the total electric flux throughout this spherical surface is equal to q by epsilon 0, where q is the charge located inside the sphere. If we consider limit delta s tends to 0, then this summation would be integration of E dot ds around the closed surface, that is equal to q by epsilon 0. So, this equation we have derived considering a sphere, but it is true, which we will prove now, which is true for any shape of closed surface, and charge may be located anywhere inside that closed surface, not particularly at the center of a sphere. This can be a generalized theorem and or a law, and this law is called Gauss law, the famous law Gauss law. This is called Gauss law in electricity. Gauss law. Like Coulomb's law, it is also a fundamental law, which states that the total electric flux around a closed surface is equal to 1 by epsilon 0 times the total charge enclosed by the closed surface. And if the closed surface does not enclose any charge, or the charge resides outside the closed surface, then this total flux would be 0. So, we can say that Gauss law states that total electric flux, that is the surface integral, this is the surface integral of normal component, because E dot ds, as I have already told, E dot ds is equal to E cos theta into ds, and this E cos theta is the normal component of electric field into ds. So, the surface integral of normal component of electric field around a closed surface, that is the total electric flux around a closed surface, is equal to 1 by epsilon 0 times the total charge enclosed by the surface. This is our Gauss law, and in mathematical form we write it as like this: integration of E dot ds is equal to q by epsilon 0, when q is the total charge, There may be number of charges, and charges are scalar quantity, we can add them algebraically, and this q gives you the total charge enclosed by this surface, where q is the total charge enclosed by the closed surface S, and it is equal to 0 if no charge is enclosed by the surface, not enclosed by the surface. So, in an electric field, if we take surface integral of normal component of electric field around a closed surface, and if that closed surface does not enclose any charge, according to Gauss law, it would give the total flux is equal to 0. This is Gauss law, and we will prove it, and it is, we will see that when we apply Gauss law, we find that it is a very powerful and convenient way to find electric field in certain situations where the charge distribution permits symmetry. We will discuss it later. Let us first prove this Gauss law for any shape of closed surface. We have sorry in fact considered as a sphere. Now, we will consider any closed surface. Suppose this is any closed surface S, and a charge q is located at a point O, and we consider a surface element ds, and A is a point, say the distance between the surface element from the charge is r, and the direction of electric field is obviously along r E, and normal to the surface element, outward normal to the surface element is n cap, this surface element ds, the outer normal to the surface element is n cap, which is the direction of the area vector ds. Now, the flux through this surface element is E dot ds is equal to E ds cos theta, where theta is the angle between this electric field and n cap, that is the direction of area and electric field, the angle between area and electric field. In fact, this ds is a cone, the base of a cone subtending on a solid angle d omega. Okay. So, a cone of solid angle d omega is intercepting the closed surface by an area ds, and it subtends a solid angle d omega. Now, what is the value of electric field according to Coulomb's law? The field at a distance r from a point charge q is 1 by 4 pi epsilon 0 q by r square. So, let us put the value of E, that is 1 by 4 pi epsilon 0 q by r square. Now, it is into ds cos theta, that is equal to 1 by 4 pi epsilon naught q into ds cos theta by r square. We have already discussed that ds cos theta is the projection of the ds perpendicular to r, and that divided by r square gives you the solid angle d omega subtended at point O. So, this ds cos theta by r square is d omega, and we get E dot ds is equal to 1 by 4 pi epsilon 0 into d omega. Now, to find the flux through the entire closed surface S, we have to integrate it into E dot ds. So, the total flux around the closed surface is integration of E dot ds is equal to integration of 1 by 4, sorry, we have left a q here, here is a q by 4 pi epsilon 0 into d omega. So, it is q by 4 pi epsilon 0 d omega over the closed surface S. This is equal to q by 4 pi epsilon 0 taken outside the integration of d omega around the closed surfaces. And what is integration of d omega around closed surfaces? I have already discussed that any closed surface will subtend the total solid angle 4 pi, a 3-dimensional angle 4 pi. So, it is equal to q by 4 pi epsilon naught into 4 pi. 4 pi cancels out, and the total flux, that is integration of E dot ds around the closed surface S is equal to q by epsilon naught. This proves one part of the Gauss law. Integration of E dot ds around closed surface, it is E dot ds, that is the total flux around a closed surface is equal to 1 by epsilon 0 times the total charge q enclosed by this closed surface S. Now, let us take the second part, when charge is outside the closed surface, no charge is enclosed by this closed surface. In that case, let us consider this as a closed surface S, and a charge q is located outside the closed surface. And if we draw a cone of solid angle d omega, it would intercept the closed surface always even times. Here it is twice. This surface element is ds1 and this surface element is ds2, and the distance is r1 here and the distance is r2 here. And what is the direction of area vectors? Here always the direction of area vector is along the outward normal. So, the direction of ds1, that is n1 cap, is along outer normal, and here it is also along outer normal along this direction. So, this is the direction of electric field, say electric field is E2 here and electric field is E1 here, and the angle between E1 and N1 cap here theta 1, here it is theta 2. So, if we want to calculate the total flux for this pair of surface elements which subtends the same solid angle d omega here at the charge q, then we have E1 dot ds1 plus E2 dot ds2 is equal to E1 ds1 cos theta 1 plus E2 ds2 cos theta 2. Okay. And what is E1? This point is at a distance r1 from the charge q. So, electric field is 1 by 4 pi epsilon 0 q by r1 square into ds1 cos theta 1 plus E2 similarly according to Coulomb's law 1 by 4 pi epsilon 0 q by r2 square, because the distance is r2 here. So, plus 1 by 4 pi epsilon 0 q by r2 square ds2 cos theta 2 is equal to q by 4 pi epsilon 0 taking common, we have ds1 cos theta 1 by r1 square plus ds2 cos theta 2 by r2 square. Obviously, both are subtending the same solid angle d omega here. So, ds1 cos theta 1 by r1 square is d omega, ds2 cos theta 2 by r2 square is also d omega. But here you see theta 1 is more than 90 degree obtuse angle. So, cos theta 1 is negative, but here theta 2 is less than 90 degree acute. So, cos theta 2 is positive. So, this would give rise to plus d omega, while this would give rise to minus d omega. Therefore, the flux through this pair of surface elements is equal to q by 4 pi epsilon naught into minus d omega plus d omega is equal to 0. So, what we see that a cone of solid angle d omega would always intercept this closed surface even number of times when the charge is outside the surface, and for every pair of such surface elements the total flux is 0, and we can consider the entire closed surface consisting of such pair of surface elements which would give rise to total electric flux as 0. Therefore, in this case our surface integral of normal component of electric field, that is integration of E dot ds around the closed surface is equal to 0. This is the second part of the Gauss law. So, till now we have discussed what are electric field, field lines, flux and Gauss law. Okay. In the next class we will discuss about the applications of Gauss law, and we will see how this Gauss law is a very useful, convenient way to find electric field in situations, in certain situations where symmetry permits. Okay. And what is symmetry? We will discuss in the next class, but we must remember that Gauss law holds good only when electric field obeys the inverse square law of force, Coulomb's law. So, both are fundamental law, both are true always, but Gauss law is extremely useful only in case of symmetrical charge distribution. Okay. Thank you very much. We will discuss in the next class the applications of Gauss law.